Alright, we're going to do some op-amp circuits. We got our first one here, and I'm going to start off by drawing this off, or just drawing it. Alright, here's the circuit here that we have gotten from the problem. Okay, so a few rules to go over about op-amps is that these two parts here and here, they are connected. They are always going to be equal. And we're going to label that as V sub A. Alright, so we have a power source here. Okay, right? Yeah, it's a power source. And we have a resistor here. We're going to call this V out over here. So what do? We can do some nodal analysis at this point. And another rule is since these are equal, the way I go about it is if I can instantly determine the value of either the negative terminal or the positive terminal, I will use that value for V sub A. Now since the positive terminal here is connected to the ground here, V sub A will be 0. So since we know V sub A, we'll plug that in for V sub A as 0. It's going to be 0 volts. So let's do nodal analysis. KCL at VA really quick. It's going to be 0 minus Vx divided by R1 plus VA0 minus V out divided by R2. And since it's 0 volts and it's connected to the ground, this is going to have no current going through it. So it's going to be plus 0 really, but I'm not going to put that. Is equal to 0. Okay. So we could solve this in terms of V sub x if we wanted to. Or no. That looks like V out. We can solve this for V out, right? Add V out over, we'll get negative Vx over R1 is equal to V out over R2. Multiply R2 over, and we have R2 over R1 is equal to Vx negative V out. That's what V out is going to be, not A. Out. And a thing to note is that this negative here shows that this is an inverting terminal. And what makes it that is because the power source Vx is connected to the negative side of this terminal on this op amp. And this is called an inverting op amp. That's what it is. Okay, now let's go to some of the problems now that we've done a little nodal analysis. Our first question asks, calculating the output voltage of an inverting op amp circuit. It gives us a few values. It gives us VCC. What is that? Well, VCC is going to be these terminals here and here. It's going to be the bounds of this op amp circuit. The top being the positive one, plus 10 volts, not negative. Oops. Plus. This is going to be negative 10 volts. Right. The range of the V out has to be in between 10 and negative 10. It cannot be greater than that. That is what VCC is doing. It's limiting it. So let's plug in what we have into our equation we have made down here. Right. So Vx is equal to 2,780 microvolts. Okay. Negative 2,780 microvolts. It's 10 to the negative 6. And R2 is going to be 7,000 over 10,000. Let's go to V out. Okay. So, if we did this, if we did 7,000 divided by, it will get 0.7 times negative 2,780, and our output will be in, if we don't change that unit, it's going to be in microvolts still, and that's going to be equal to, let's check the answer, where's my phone, 2,780 times points that we get 1946. It's going to be negative 1946 microvolts. Which rounds up 3 significant figures, we'll get 1950, just like the answer intended. And let's figure out R2 if we're given such values. V out, it's telling us that M is equal to 36. Okay. R1 is 7.8. And VCC is equal to 5 volts is our limit. Okay. Alright, so we're given R1. That's plenty. That is plenty. So for this problem, what is M equal to? 36. And R1 is equal to 7,800. Well, what is M? What will M be? Well, notice the place of where M is at. That's what M is. It's just replacing R2 over R1. So, if we plug that into an equation, R2 divided by 7,000 is equal to 36, which is M. That's what M is equal to. Multiply 7,000 over, and we get R2, which is going to be 252 kiloohms. Well, that's not right. Did I multiply it right? 2,800. Ah, see, that's where I messed up. 0.8. Ah, okay. Yeah, I multiplied it by 7,000, not 7.8. My mistake. Times 7.8 is equal to that. 0.2. Okay. And that's going to be our R2. Okay. Now let's do our next one. Saturation. Well, saturation, what it really is when you have VCC. If the output tries to exceed that, then it's going to limit it. That's when saturation occurs. So determine the positive value of Vx that will lead to saturation in the op amp for figure 1. Well, how would we do that? Well, we already have our equation here, right here. Let's copy it over. I'll start off with a new slice here of paper. And here it is. Okay, so how do we determine saturation for Vx? What do we need Vx to be so that VCC, or the saturation point, is reached? Well, saturation happens at 10 volts for the output. So let's plug it in. So set V out equal to 10. And what's our R2 and R1 going to be? Well, using your answer from part B, we're going to use our previous 280.8 for R2 and 7800 from part B. So we're going to pull our numbers from part B. We're going to have these in kiloohms. Alright. So whatever number we get here, let's divide that over. So this divided by 7.8. You get 36, which is what our M is. So it's going to be negative 10 over 36. Which we get negative wait a minute. I see where I messed up. See, this is not 10, and the previous problem B is 5. Right? So, we're dealing with the number 5. As you can see, VCC is 5 from part B. We're using part B. Alright. So this is 5. Well, what's the positive value for Vx? We don't want Vx to be negative, so VCC is from negative 5 to positive 5, so we'll make this negative so this becomes positive. So, that'll give us 0.139. Is going to be the Vx saturation point. Volts. Okay. Let's go to the next question. Alright, let's draw this amplifier really quick. Alright, now that we've drawn this circuit, now that we've talked about this before, these points are equal. This one's connected to ground, so we know that this one on the bottom is going to be 0 volts, or the one on top, the negative terminal. It's going to be 0 volts here. So let's do a nodal analysis, like we did in the previous. So we're going to do a KCL of 0 minus V1 over R1 plus, we're just going to call it negative V2. It's 0 minus V2, but I don't want to keep writing the 0. Plus negative V3 plus negative V out over R4 equal to 0. Now let's solve for V out, since it's our important point. We're going to get it on the other side. It's going to be V out. We're going to add it over. We're going to get V out over R4 is equal to, let's factor out that negative. We'll get V1 over R1 negative plus V2 over R2 plus V3 over R3. Okay, so let's expand that a little. Now let's multiply R4 over. So we have negative R4 plus, and here we'll have V1 over R1 plus V2 over R2 plus V3 over R3 is equal to V out. Okay. Now that we made the equation for this circuit, this is a negative. It's connected to the negative terminal, so it's an inverting amplifier. But you notice how we have all of these all added together? It is a summing inverting. Alright, now that we have our equation here, notice how you have multiple voltage sources. That means it's a summing inverting amplifier. We got the negative, so it's inverting. And we know it's inverting here too because it's connected to the negative terminal. That's where the power comes in from these three. Okay, so let's go back to our questions. Let's go to the first question that uses this figure. Okay, so these are a bunch of numbers you can plug into that formula we made, and then you'll get V out. For the time being, you can plug that in to make sure the formula is right. It definitely should be. We're going to go to the next one. Let's see how to solve that. Okay. So this gives us M1, M2, and M3. And it tells us RF. What is RF? RF is what our R4 is. Okay. So, it's basically telling us that when you multiply R4 over, that's going to be R4, over R1 will be equal to the M. Let's say M is 5. And RF, which is our R4, is going to be equal to 120. Now let's swap these. And we get 120 divided by 5, which is equal to 24. So R1 is going to be 24,000 ohms, or 24 kilo ohms. And that's how we do all the rest of them. For example, we'll do the next one. 8 is M2 is M. So if you have M equal to 8 equal to R4, which is that one, which is RF, over R2, let's say. So 120 divided by 8, that'll give us 15, or 15,000 ohms. Okay, let's go to the last one. Figure 2. It's the same one, except it's asking us to determine the range, maximum, minimum values of V1, such that the op-amp operates in the linear region. Assume that R1 is blah blah blah, R2 and R3, RF is equal to that, we're in V2, V3, and the limit is 15. So since our limit is 15, that's going to be our maximum for V out. So VCC is going to be equal to V out. And then we'll plug in the rest of the numbers. So what we're really solving this for is V1. So let's rearrange the equation so we solve for V1. Okay. Here's our old equation that we had. Let's manipulate it so it works for us. Okay, so we're gonna do a quick some quick. We're gonna add that over, then multiply by R1, and then we're gonna factor out these negatives here. So to do that all in one move, and we're gonna multiply that R1 over. So it's gonna be V2 over R2 plus V3 over R3 plus V out over R4 is equal to V1. Okay, so VCC is equal to 15. Well, there's a negative 15 and a positive 15 value because this VCC is going to be from negative 15 to positive 15. And our answers will vary depending on that. So, how you solve this problem is you're going to plug in 15 first for V out, then plug in the rest of your numbers to solve for the maximum V1, then plug in negative 15 to solve for the minimum V1 for V1. And then you'll get that answer hopefully. Okay, we'll do the next one. Next problem. Let me draw this circuit really quick. Okay, now let's write an equation for this circuit. Now that we look at this op-amp, we can see that the terminals on the negative and positive don't give us a distinctive value for what I'm going to call as these both V sub A. Doesn't really give us one right off the bat. So let's solve for one. Let's do a KCL, the one that has almost nothing connected to it. And we're going to see something interesting, slightly. It's a little interesting. And it's a neat little concept. So V sub x minus the voltage going over V sub A divided by R2. Alright, that's the only current going that way. It's equal to 0. This will be the current. That'll be the current this way. Well, let's solve for V sub A. So V sub x over R2. Let's add the V sub A over R2 over. And we get, if we multiply both sides of R2, V sub x is equal to V sub A. Well, that's a little interesting. Well, another one of the rules about op amps is if you want to solve, we're going to call this a power source, and this is going to be ground. We could rewrite this up here as something like this. This is an example. This is going to be V sub x. Something like this. Okay. Well, this is a circuit, a closed circuit. Well, the point here is going to be V sub A. What we did is we cut off that circuit up top and we made it a nice closed circuit. And this all on here is going to be ground. So what we did is we, what is the word? We didn't short circuit it. We made it an open circuit at the point up top here at VA. Okay. And you could redraw it as this down here. Actually, no. We're not going to use this example, but I'm going to keep going with it. So, an interesting concept is in a circuit like this, the voltage that goes across this R2, you would think there's going to be a voltage drop there, but after it passes through Vx, or it passes through that resistor, all the voltage, when you read it on this side, is going to be equal to Vx. Because after it's passed through that one resistor, you're only connected to the battery. Well, it's going to, like, this, this is all, like, there's nothing separating that part from the battery if you were to travel through the circuit freely. It's a little weird to think about, but the rule is that, well, let's use another example. Say you have two resistors. Okay, how is this any different? Well, if you had a battery here, and they're connected, say there's a voltage drop across this, like as if you do the current times resistance, and you get like 4 volts, right? And this is 20. Well, this point here is going to be 20 minus 4 because there's a 4-volt voltage drop, and you're going to get 16 at that point. Now this next resistor has to get rid of all the voltage no matter what. If you don't know what this is, if we make that an unknown, it's going to be, we'll call it 16 ohms, or it's going to be a 16-volt drop. So this is going to be 0 over here, 0 volts. Now once you reach 0, after passing through all the resistors, when you try to read the voltage at these points, it's going to be equal to 20 volts. Right, if you were to take a multimeter and read it. The reason behind that is that there's no resistor stopping the voltage or slowing the current at those points. Basically, if it's connected to ground. Ground is 0 volts, but after it's passed through those resistors, it's going to be equal exactly to the power source before it. But well, we're gonna keep it at the nodal analysis um, as to why they're equal. So yeah. So Vx is equal to Va. So let's continue. Let's do a nodal analysis at this point up here, and we're going to get Va over R1 plus Va minus Vout over R3 equal to 0. Solve for Vout. Add Vout over R3 over. Multiply R3 over. We're going to get Va. We'll factor out Va too. We're going to get R3 over R1. And R3 over R3 is just 1. So this is the equation we get for this non-inverting amplifier because the power source is connected to the positive terminal. And that's how we solve for that. I know I talked a lot about this, but it's important to know as to why it's like that. You can just do a little Vx minus Va or Va minus Vx and solve for Va. Doesn't matter which way you do it. You'll end up with Va equaling Vx. Okay, so let's solve for part A. Determine V out when blank 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 blank. Okay, so just plug those in. You'll get your answer. Okay. Hmm. Determine R1 such that V out is equal to M times Vx. M is 5. Well, let's look at the bar here. M times Vx. Well, VA is Vx. And our M is going to be this whole portion here. Because it has to equal V out. And our equation has to equal V out. So, we know R2 and R3, it's given to us. Let me think. Well, we have all we need, right? Determine R1 such that, okay, we are, yeah, this is what we found here. That's our expression. Okay, so we have R3. They give us, no, that's wrong one. They give us R3. We need to find R1. And they give us also R2 and M. And M is equal to 5. Yep. So we could say 5, which is M, is equal to R3 over R1 plus 1 is equal to M, which is our sub. And we know R3. So we just solve for R1. Subtract that 1 over. We'll get 4. And then swap the 4 and the R1. And we'll get R3 over 4 is equal to R1. And what is R3? 85. 85 divided by 4 is 21.25, which gives us, if you round it, it's 21.3 kiloohms. And that's all the problems. Yippee!